valuable than oil or gold. Something wars are fought over, something economies are staked upon, and something that we require for life itself. Who'd have thought it would be something as basic as fresh water? And now we're running out. Worldwide, river basin systems are being overexploited for agriculture, municipal use, and a host of other functions. And sadly, New Zealand is not immune from this. Think back to February of this year, and no doubt you'll be remembering weeks and weeks of unbroken sunshine. But the reality was, our entire nation was hit devastatingly by drought. Satellite images depicted a shocking contrast to last year as our whole nation turned brown. Even more appalling, the revelation that Wellington had only 20 days of water left in her drinking supplies. Our capital city. The only contingency plan was to suck an extra 17 million litres from the Hutt River to survive the drought. This was an extreme situation, but it wasn't the first time that excessive abstraction was seen as the solution to water shortage. Campbell Live ran this article on the Selwyn River in South Canterbury, which increasingly is being used as a source for abstraction of irrigation water to power the dairy industry boom. The result has been disastrous for the trout that used to swarm upriver to spawn, with numbers plummeting from an estimated 60,000 in the 1960s to 184 fish today. But let's take a look at it from the dairy farmer's perspective. They drive our economy. New Zealand is the largest dairy exporter in the world, and they need water as annual precipitation slacks off or becomes less reliable. Using surface water supplies to keep fields green seems an obvious solution. So clearly something isn't working. We desperately need more water for our rivers, our farms, and our populations living in the cities. So I'm going to run through a few of the current inadequate solutions and outline a few new and exciting innovations that may just hold the cure to this chronic water shortage. Hard engineering has been the traditional approach to water control. However, increasingly it's seen as expensive, vulnerable to failure, and having a high negative impact on the natural processes of the environment. With 97.5% of the Earth's water being salty, desalination seems the obvious alternative. However, it too has serious obstacles to overcome. For most of us, the word desalination is inextricably associated with astronomical energy requirements and cost. Let's briefly discuss the two most common forms of desalination: multistage flash distillation and reverse osmosis. Multistage flash distillation produces approximately 85% of the world's commercially desalinated water. Water is flashed into steam to progressively remove the salt. Obviously, this is an expensive process. The high specific heat capacity of water makes boiling it an incredibly energy-intensive task, despite improvements in engineering. Reverse osmosis, a membrane-based process, involves the use of pressures of more than 1,000 pounds per square inch to force water through a membrane to exclude the salt, which is cheaper than boiling it, but still incredibly energy-intensive, no matter how refined the engineering becomes. The concept of cogeneration involves coupling desalination with power stations to increase efficiency and reduce costs. However, the power generation options themselves come with serious issues. Fossil fuel power sources creating greenhouse emissions, nuclear power sources being politically and environmentally unacceptable, and wind power having a huge footprint and huge cost. These are not viable options for New Zealand for political, environmental, and economic reasons, and we're left searching for a radical new solution to meet our increasing water needs. Perhaps we need to be thinking smarter, not harder. Perhaps we need to look at groundbreaking, revolutionary work being done in chemistry and biotechnology and find new ways to apply it. Perhaps we need to look at the expanding field of biomimetics, a concept which revolves around copying nature's supremely efficient designs. Already, we're using it for sophisticated innovations, like taking the microscopic corrugations from the eye of a 45-million-year-old fruit fly and incorporating them into anti-reflective structures on solar panels. And this is impacting on our ability to engineer smart biological membranes, creating the potential to link with desalination in massive ways. Carbon nanotubes are one such area that links to desalination. Purportedly more successful than current reverse osmosis membranes, there are also remarkable discoveries, like the addition of hydrophilic functional groups around the mouths of the tubes, which are upping their potential. As research and discovery continues, no doubt their viability as an economic option will increase. But even this is playing it relatively safe in terms of technology and innovation. What I want to propose is bigger and far more fantastic. We need to look at the carefully honed process of purification that happens in kidneys and desalination glands across animal species worldwide and think, why can't we mimic it? Why can't we take our inspiration from the structure within the kidney, the nephron, which would negate the need for high heat or pressure, and thus high energy and high cost? The nephron contains a region named the loop of Henle, which is adapted to reabsorb as much water as possible from urine before excretion. And what makes it of interest to us is its membrane components, adapted to actively transport Na+ and Cl- ions out into the surrounding solution. That's what makes nature's membrane superior to ours, the ability to intelligently select the salt ions out of solution and actively pump them against a concentration gradient. So what we're saying is we need the membrane structure of the epithelial cells that line the loop of Henle to be exactly recreated with the correct proportions of the correct channel proteins and biological ion pumps. And with new gene technology, that's entirely possible. Introducing induced pluripotent stem cells, basically man's template from which he can artificially create any kind of cell he likes, provided he's got the right genetic material. Sure, they still have some issues, like the unfortunate habit of getting cancer and dying by apoptosis. But already new DNA manipulation techniques which avoid the use of viruses as a vector have seen significantly fewer genetic anomalies. So right now you're looking at me going, okay, that's great, Katherine, but you're talking about growing some cells in a petri dish. How is that going to solve New Zealand's water crisis? So let's enter one of the fastest growing technologies of our modern era, one that's revolutionizing manufacture and design at an astonishing rate: 3D printing. And for us, it's 3D printing's application to medicine that's one of its most fascinating aspects. What people like Dr. Anthony Atala are doing is simply mind-blowing. He leads the Wake Institute for Regenerative Medicine and was one of the team to first 3D print a human organ. Yes, he made that kidney up there. How the heck did he do that? That's incredible. And it all comes down to this: we can 3D print stem cells. Actually, what Atala and his team can do is better than that. They first print a base structure, a scaffold, made of a smart biodegradable material, onto which can be printed or embedded cells which can be differentiated into the tissues required. Isn't this exactly what we need? We can 3D print onto a supporting structure cells which can be differentiated into the epithelial cells that line the loop of Henle. We can replace reverse osmosis membranes with living tissue which performs the same function, minus the intense pressure. We could print them as a cylinder, which could act as a pipe through which the water could flow. Maybe we could even use enzymes to lyse and rejoin the cells as a flat surface without cell contents. There are so many different options to make it work. But things are moving further than that with 3D printing. We're now at the stage where we can do this. This is an image from a scanning electron microscope of a 3D printed microscopic Formula One race car. We now possess the technology to print objects smaller than the size of your average bacteria cell. And this is opening up incredible new membrane possibilities. Imagine if we didn't have to print whole stem cells. Imagine if we didn't have to inject them onto a scaffold, differentiate them, and upkeep them as living tissue. Imagine if we could just print the parts of the cells that we needed. Imagine if we could print the exact membrane, not even necessarily a phospholipid bilayer, perhaps a polymer or composite structure that would be stronger, embedded with the exact channel proteins and ion pumps that we needed for desalination. The possibilities are endless. So there is potential in the field of biomimetics to create amazing new technology and design. So why should we sit back and let other people do the research? Why couldn't New Zealand students and scientists take the lead? I believe that this is an area which desperately needs investment so it can yield incredible new discoveries in more than just desalination. There are lessons to be learned from nature's structures in every conceivable facet of science. But even if we only look at desalination, there are still considerable gains to be made. A constant stream of municipal water to towns and cities would remove the dangers of urban water shortage. A steady supply of irrigation water to farms would reduce the impacts of long dry summers, reduce irrigation costs, and potentially boost profits through an increase of feed and quality of stock. And a reduction in abstraction from natural sources would benefit ecosystems nationwide. Something more valuable than oil or gold. And the sooner we invest, the sooner we can begin to reap the benefits. Thank you.
Questions?
Thanks, Katherine. I'm your designated questioner.
Excellent.
My learned colleague, first of all, how crucial is the 3D concept to your presentation?
The 3D concept is definitely taking it a step further into the hypothetical. Even if you only look at already sort of known technologies such as the carbon nanotubes, there are significant potential in those areas that don't necessarily involve the 3D printing. However, it is a fascinating new aspect that we can look at that technology has given us and that is developing at such an incredible rate that it would be crazy not to use that technology wherever possible to
Indeed.
benefit.
But as my learned colleague pointed out, 3D printing of DNA, 3D printing of cells and their chemical structure is extremely hypothetical. Accept that?
It has been done recently, like even in a couple of weeks ago in the Stuff magazine on the website, there was an article about a 3D printed liver which was implanted into a patient and is functioning. So it's definitely current. It's not purely hypothetical. There is evidence to support that it will continue to develop.
You've obviously very keen on both science and arts. How would you improve the science and technology education at schools? What's been your experience?
I would say that, having been to a couple of different schools, I would say that teaching is the most important aspect of teaching science. So I would say that the most important thing for a student learning science is the enthusiasm of the teacher.
Have you had good ones?
Definitely. I've had some of the best teachers, so I'm very grateful for that.
Very good. Your check's in the mail. Thank you. Cheers, Katherine.
Awesome.
Ladies and gentlemen, Katherine Eichelbaum.